Okay, we'll go ahead and get started. Okay, so on CCLE, I just, late last night, I created the Kaggle competition. And I want to run two competitions, so one for classification and one for regression. And that way all of your eggs aren't in one basket, and like if you do great on both, that's great, but if you like totally do bad on one of them, like it's only half the points for the kind of the final project, right? So so anyway, I think I created this Kaggle competition correctly. This is my first time running a Kaggle competition, so I hope it's right, but we'll find out. Please be patient with me in case things go wrong. Okay, but I think it works well. Has anyone done a Kaggle competition before? Okay, all right. Oh, okay. A lot of you have. Okay, so you're familiar with how they kind of structure. You get a training set where the answers are provided, and then you get the test set, which is basically the same thing, but a column is missing, right? And then you make predictions on the test set, and then you upload your predictions. Okay. The data set I've chosen for this classification competition, I purposely chose, I don't know, maybe this was a bad choice on my part, but I purposely chose one where there's actually more predictor variables than there are observations. So there's a total of 126 observations, 88 in the training set and 38 in the test set, but there's 309 predictors, okay? And so you will have to do some figuring out of how to kind of reduce the number of predictors, because obviously if you use all 309, you can predict all the values perfectly, okay? But that means you've probably overfit the data severely, okay? So you're gonna have to do something to kind of reduce the number of predictors. It's based on a real life thing, and so make sure you read. Oh, okay. Yeah. All right. So make sure you read this journal article from from IEEE. Okay. And so you should be able to download it for free while you're connected to the UCLA network. Okay. If you go home and you live off campus, then make sure you VPN in. Otherwise, you won't be able to access the article, right? So, UCLA subscribes to that journal publication, and okay. So anyway, this is going to be your training and your test data sets, okay? And you'll see all of the predictors. And basically, this is based on some speech. I don't know, software or something. Okay, so people. So people with Parkinson's disease, Parkinson's is this, neurodegenerative disease, as the disease progresses, the person's ability to speak worsens, and they become more and more difficult to understand. And basically, can we understand you is a little bit subjective, right? Like, I listen to you and I can understand, and but as things get more garbled and muffled and things like that. But anyway, they have some software, and basically they have the people talk, and then the software just records stuff like jitter and shimmer, and I'm not a speech therapist, so I'm not 100% sure what exactly these things mean. I did read through the paper, and it has something to do with kind of like, the microphones, they pick up the frequencies and stuff in the speech, and they just kind of analyze like something, and it produces a number, okay? Now, if you search for this paper and stuff, you'll find the original data. I've kind of added a little bit of noise to the data, and a little bit, and I've kind of scaled the data and stuff it should not affect your ability to make predictions. But I did that just so you don't try to like backwards engineer the answers, because if you find the original data set, all of the data points are labeled, right? And so I didn't want you guys to try to like find the original data set and try to backwards engineer the answers in the test set. So I had to purposely try to obscure it a little bit. It shouldn't affect your ability to make predictions. I think in the article they were able to achieve around a 90% cross-validation rate. That's not by no means a target, okay? Don't feel bad if you can't achieve that, okay? The base rate though, okay, you do have to beat this, is like 70-something%, and that's if you just predict class 2 on every single observation point, okay? So you have to beat that, okay? Your model has to be just predicting class 2 for everybody, because I think there's around a 70-30 split on the test cases. I've given some instructions here regarding the project grading guidelines, okay? And so there's going to be 2 projects. So far, I've only got the classification project up and running. This weekend, I'll work on the regression competition, and I hope to get that up by the beginning of next week, okay? And basically, each one's going to be 16%, so you're a total of 32%. And your grade will be part report and part performance, okay? And I was debating how much to put on each side. I ultimately decided 4% will be competition performance. And the way it's going to work is first place teams tied for first place will get 4 points, and then last place will get 0 points for this out of the 4 points, and everybody in between gets something kind of scaled, just a linear scale based on your placement, okay? So if there's like, and you can work in as individuals or in partners. Yeah, question.
Both of them placing first place.
Yeah, then both teams will get 4 points. Yeah, so whoever's tied for first place will get 4 points, okay? And then whoever's tied for second place will get the same amount of points. So here I said, let's say there's 12, like, I don't know, there's however many of you, but let's say because of ties and things like that, there's 12 unique positions on the board. Then 12 positions means there's kind of 11 gaps, and then so each gap, it will be 4 divided by 11 or something like that, okay? And the scaling will basically go like this. So that's just an example. I don't know how many unique positions there will be on the board, and again, you can choose to work individually or in partners, things like that. When you pick your team name, just put your first name, okay? Creative names are fun, but just to kind of keep things simple for me, just use your first name, and then that will be fine, okay? You will have to submit the R script that you use to generate your predictions, okay? And this is, and I'm going to verify that indeed the R script you run produces the predictions you used in the competition, okay? And the reason for this is I don't want people to like run some kind of model and then they get predictions. And with Kaggle, all you do is just upload the prediction file. And so technically, you could just manually change a prediction in your upload file. And so even though the model predicts 2, like just kind of by trial and error, you could like change that to 1, and then it might gain you extra points in the leaderboard, okay? But I don't want you guys doing that. That's like cheating, right? So so you need to run the model, and whatever model predictions your model makes, that needs to be what you upload to Kaggle, okay? So just so we don't have people kind of gaming the system, because so normally Kaggle has a way to kind of prevent the gaming by having the public leaderboard determined by a certain subset and a secret hidden private leaderboard determined by a different subset. But because I only have a total of 38 observations in the test set, I didn't want to like further split that into a public and private. So basically all 38 observations are used for the evaluation in the public leaderboard and the private leaderboard. So there's going to be no mystery. What you see on the public leaderboard is how you will be ranked at the end. But at the same time, I don't want people trying to game the system by just manually making adjustments to kind of tweak their position on the leaderboard, okay? If you're going to try to tweak your position on the leaderboard, it has to be done through the modeling and not through just manually changing the prediction answers. Okay, does that kind of make sense? Okay, and then the report, keep it around 2 pages long. I don't want to be reading like giant things, okay? And basically it just needs to cover anything you did to the data before you fit the model, okay? So if you did any kind of data transfer, and I just kind of listed off some things that you might do. You don't have to do any of these things, all right? But if you do any of these things, you have to talk about it, okay? So, so you need to talk about anything you did to the data before you fit the model, and then talk about the model that you fit, any kind of things about it, and then the last will be why you think your model is good or bad or whatever, ways to improve it. Okay, shouldn't be too hard. I tried to make a rubric to kind of explain how the grading on this portion will work. Anytime you have a written thing, there's a tiny bit of a subjective component, and I'll try to I try to make the description clear there, but that's what we have there. Okay, are there any questions? I think this is basically what I've included for the starting template. Just kind of import the train and the test, and your model is going to be based on the training data, and then you're going to make predictions on the test data, basically, right? And then so here right now the bad predictions is just 2 for everybody, for all 38, and then the test IDs are 89 through 126, and you just kind of bind them together, and then you write the CSV file this way, and that should allow you to upload it to Kaggle for evaluation. I think Kaggle limits you to, I think it's limited to 1 upload per 24 hours, okay? So, what's that? Okay. You want me to change it? Okay, maybe in the beginning we'll start with 1, and maybe as I don't want people to constantly just like do one little thing and then upload and try to check that way, right? Like we should have some kind of internal. You should be using something like cross-validation within your training data set to kind of decide, like, is this a better model or not, right? Something along those lines, okay? We'll see how it goes, okay? We'll see how it goes. And I don't know. I hope it's interesting. I hope it works out. Okay. Again, first time running it. I hope the data set. I'm always a little bit nervous that like the data set I picked was no good. Okay. Did everyone respond to this online poll? Everybody's good. Okay. I'm gonna go ahead and close it. And okay. And then today we'll talk. Chapter 7 in the other thing, okay? I saw somebody wrote on CampusWire that maybe they prefer when I don't use slides, so I don't know. Okay, but we'll see how it goes. I have slides today, although like some of the slides I've got to fix. Okay. All right, so on Monday we talked about linear model selection, regularization, all of that, and then today in chapter 7 we're going to talk about fitting things that are not linear, right? So far we've kind of talked about multiple linear regression a lot, and I know you've covered that a lot in 101A, but here we'll kind of make things a little bit more complicated by allowing for non-linear relationships, okay? So, your multiple linear regression looks something like this, right? You got all of your betas and all of your x's and things like that. And probably the easiest step for multiple linear regression is something along the lines of polynomial regression, right? And so here, you can have a relationship with like one of the x's and one of the x's squared and another x cubed, okay? And then you can have another different x variable and have that first order and second order and third order and things like that, and some kind of nonlinear polynomial relationship here, okay? At the heart, we call these additive models, okay? Additive because we're saying y is the result of taking this thing and you add this thing and you add this thing and you add this thing, okay? And so it's the result of just adding a bunch of numbers together, and those numbers are going to be, either x or x2 or, x3, or maybe you square that or cube that, or you multiply it by some coefficient. But the end result, y, is the result of adding things together, okay? And that's that. It's a little bit different from like, so that's an additive model, different from like a logistic regression model where you have kind of the linear part and then you put it into a function and it transforms that function, okay? Now, technically, we could get to that also because logistic regression is called the generalized linear model. So inside it, there's a linear part, and then you generalize it by sticking it into some kind of transformation function. And then in the same way, we can start off with an additive model, and then we can generalize it by taking the additive part and sticking it into some kind of transformation function as well, okay? But we'll just start off focusing on the additive part. And so far, we've just had the linear stuff, right? And so with the linear thing, basically the idea is that, if x1 changes by 1, then your prediction goes up by beta 1, okay? And if x2 changes by 1, then your prediction goes up by beta 2. And this relationship holds for all values of x1 and x2. So whether x1 is small or x1 is big, if x1 changes by 1, your prediction goes up by beta 1, okay? And that might make sense for things like how much money did you spend at the grocery store and how many, how many apples did you buy, right? Each apple you buy is going to add, 70 cents to your grocery bill or something, right? Or I don't know, how much is an apple, okay? So, if you buy 2 apples, it costs 70 cents more than 1 apple. If you buy 12 apples, it costs 70 cents more than buying 11 apples, right? So that makes sense, right? But something like if we're talking about age and height, okay, when you're a kid, each year that goes by, you grow by, few inch, like an inch or a few centimeters or something, right? And there might be a linear relationship when you're a kid, right? Going from 5 years old to 6 years old, you grow this much, and going from 8 years old to 9 years old, you go up by around the same amount, maybe, I don't know, okay? But that linear relationship does not hold throughout all of your life because, going from 25 years old to 26 years old, your height is probably going to change 0, right? Or, I don't know. Do people change heights when they're 25 years old? Probably not, right? Do they even, maybe it goes down? I don't know, right? So it's not a linear relationship, right? When you're young, when x is little, the height goes up with each year that goes by, but at a certain point, it stops, right? And so a linear model is not going to work for something like somebody's height, okay? Because so that's just not going to work, okay? Okay, so what we are going to do in today's class is that we're going to remove kind of this linear relationship. We're going to say, it doesn't have to have this nice thing where every time x goes up by 1, we're going to go up by this amount, right? They don't have to be linearly related. We're not even going to make them be polynomially related. We're going to just allow for arbitrary relationships, okay? Now, we can keep a mathematical function, but we'll actually get to a point where it doesn't even have to have a mathematical function. The only thing we're going to try to enforce is we're going to try to make the thing smooth, okay? That's what we'll try to do, okay? And when we call it an additive model, our prediction for y will be the sum of kind of the smooth functions or something like that. Okay, so this is just like a silly thing. So we could imagine here's x1 and here's x2 and here's x3, and for x1 maybe the relationship between x1 and y is this, and for x2 the relationship is this, and for x3 the relationship is this. And let's say okay, and so what we see for x1 is that from 1 to 4 there's like this might be like something kind of like height, where in the beginning it goes up a lot, and then at a certain point it kind of levels off and then maybe starts to go down, right? So this could be something like I don't know, torque on a car, right? Torque is like how much power your engine can give to the wheels, and so like if the engine is spinning slowly, like you have no power and your car's not going to move. And then the harder your engine revs, your tires can spin more, but at a certain point it kind of levels off and actually goes down, and things like that, right? So we have this kind of thing, and I don't know, this is something different, and basically if x1 was, say, 8, and at 8 we would predict, I don't know, 6, and here at 8 we would predict something like 2.5. Oh, okay, wait, I don't have an 8 over here. Okay, but 8 would probably be something like 12, I don't know. Okay, and you would add those parts together and to get your prediction for y, okay? So that's kind of where we're headed, and for now we'll just kind of talk about maybe the different kinds of shapes that we can do. So we'll start off with polynomial regression, okay? And I think we're pretty familiar with this already, okay? And again, just like anything else, the more terms you add, you get more and more flexibility, all right? But too many terms will lead to overfitting. We don't want that, okay? Polynomial regression, an issue with that is extrapolation, right? So with if you have a polynomial of a high degree, they tend to just shoot off very rapidly, okay? And especially outside of where the region is fit, right? So you might have collected data inside this region, and with the polynomial fit, you get something that fits your data quite nicely, okay? But with a polynomial outside of this thing, it's gonna like rapidly take off. It can accelerate up or down or something like that, okay? So if you think of like, something x to the 10th power, okay, maybe it fits nicely for the data, but then as soon as you start extrapolating and trying to predict values where you have not collected data, right? So you fit data for 1995 to 2018, okay? And you have some kind of relationship with year, and it fits this nice thing, and you can say, okay, so a polynomial fit, you can say, all right, we missed collecting data in 2003, but we have 2002, we have 2004. You can kind of interpolate the value for 2003, okay? but your data collection ended in 2018, and if and let's say you want to predict what's going to happen in 2025, okay? The polynomial is going to, trying to use this to extrapolate what will happen in 2025 is very dangerous, because that polynomial can just rapidly accelerate up or down or something like that. So polynomial regression is not good for extrapolation, right? Even linear regression, it's dangerous to extrapolate, because you are assuming the same linear relationship will continue to hold for the next 10 years or something, which may or may not be true, right? We don't know exactly what will happen in the future. And so with things like climate change and stuff, it's hard to know what's going to happen in the future. And as far as we know, what could happen is that it accelerates and the global temperatures rapidly increase, or it could kind of slow down. We're not 100% sure, okay? Climate scientists are all kind of in agreement that it's going to keep going up, but the rate at which it's going to change in the future is unknown, and that they have upper and lower bounds for what could happen, but who knows, right? Predicting the future is always hard. Okay, only after we've looked at the past we can go, oh yeah, this was the trend that was fitting. But predicting the future, we don't know if it's going to shoot up like this, or if it's going to just keep linear, or maybe it'll level off. Probably not going to just level off on its own, but who knows? Okay. All right. So anyway, estimating the coefficients. This is just blah blah blah. Like linear regression. Okay. So you just kind of you can fit LM, and you can try to just minimize the squared residuals. Or we learned shrinkage methods on Monday. You can use any of those things as well. But basically, the way you fit a linear model is going to be similar to the way you fit, one of these, like a polynomial model. Okay. When we do this, one thing that we could do is we could just take your x variable, and then we can just square it and cube it and things like that. An issue with that is you're going to get values that are highly correlated in terms of when x gets bigger, x squared gets bigger, and x cubed gets bigger. So there's a function called poly in R, and that's going to kind of create these linear combinations so that that they don't do that. And so if you use poly, they're all uncorrelated, and you get, this is your linear, this is your quadratic, the blue is the cubic, and the green is the fourth order polynomial, right? And so these are all uncorrelated, at least on this boundary of x. Okay, now if you expand that, these values will all be correlated positively. As x gets bigger, these values all get bigger, things like that. Don't worry about this, okay? Basically, R handles all of this stuff for us, and basically the predictions that it makes using poly, the predictions that it would make would be the same as if you used x squared, and x cubed. Okay, the values of the coefficients that gets estimated with LM or something would change drastically, but the coefficient, but the predictions after you add everything together would be pretty much exactly the same, and then the statistical significance of the of each degree polynomial will also be the same. Okay, and so if you just do the traditional way of taking x and raising it to the fourth power, and it turns out that that's not significant, using poly, where it creates this fourth order polynomial here that will also come out to be the same in insignificant degree, okay? So here, I've created a fake data set where I've just taken the values 20 through 60, and y is related to a squared distance, right? So y is distance squared plus some random noise, okay? And I've put like lots of noise, standard deviation 200, okay? And here I say, okay, fit a linear model, and then we're gonna do poly 2, so this is a quadratic, and poly 3, this is gonna be cubic, okay? And then, there's a few things you can do. One is you can do ANOVA and compare the three models. And here, basically, so starting off with just one, we get this is our RSS. And then going to the squared fit, it's very significant, okay? There's a huge reduction in the RSS going from a linear to a quadratic fit, okay? And there is, the more terms you add, you can always reduce your RSS, but the difference between going from the quadratic to the cubic fit, that difference in RSS is not significant, okay? Which makes sense, which aligns with what we've done with our data generation, is that there's a quadratic fit, and so it does say that going from linear to quadratic is significant, but going from quadratic to cubic is not, okay? And so so that's what we have there, okay? And this is kind of the difference. Red is the quadratic and blue is the cubic, and you can see that the blue fits the quadratic almost the same or something, right? And just eyeballing it, it doesn't even look like the linear fit is all that bad, but it does make a difference. So. Okay. So that is polynomial regression. I think that's fine. Okay, we can talk about step functions. Okay, so a step function basically looks something like this, right? So you've got these dots, and basically a step function says, okay, for this interval, we're going to fit one value, and then for this interval, we're going to fit another value. For this interval, we fit another value, and for this interval, we fit another value. Okay, so a step function just says, I guess it's kind of like, how much money do you make? This is how much you pay in taxes, right? Or something, I don't know. This is what your tax rate's going to be, right? And then how much money do you make over here? Like, you get kind of a step. It's actually, that's not a strict step function. It's a little bit more of a linear thing. But yeah, it's just kind of, for people within this range or within this value, we just predict the same value for everyone. And then within another value, we predict the same value for everyone, and something like that. Okay, so this is kind of what the step function looks like. We have these these cut functions. Okay, and it basically says, this cut function is equal to 1 if this statement is true. So if x is less than the first cut point, it's 1, and it's 0 when it's not. Okay. And this is basically, you get C1 if x is between cut point 1 and cut point 2, and then you have C2 is true when x is between cut point 2 and cut point 3, okay? And then, and the model is beta 0 plus beta 1 times C1 plus beta 2 times C2 plus blah, 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 up to the kth kind of cut region, okay? And so what this looks like is that, this is beta 0, okay? And then at this point, okay, between C1 and C2, it takes on this value, beta 0 plus beta 1, okay? And so it pushes it up here. And then between C2 and C3, it's going to be beta 0 plus beta 2, okay? And then for things bigger than C3, it's going to be beta 0 plus beta 3, okay? Because it takes on, it's a 1 or a 0, and everything's basically a 0, or it's a 1 if it's within that certain region. Okay, so this is how we do the cut points. All right, and so the thing with step functions, the question is, okay, well, where do I make my cut points? Okay, and the answer is there's no clear-cut way to do this. Okay, arbitrary. Okay, generally it's arbitrary. Sometimes you can do like you can use kind of percentile functions, and you can say I want 5 cut points, and we'll do the bottom 20%, middle 20%. Or not, whatever, the next 20%, the middle 20%, the next 20%, the top 20%, or something like that. You can do that. I guess that's only 4 cut points. Or maybe there's something that kind of systematic that makes sense. So you might say, like, we'll do a cut point between grade school and middle school, and a cut point between middle school and high school, okay? Or, for marketing, like when advertisers are talking about ages that they're targeting, they have arbitrary cut points. They're targeting ads for kids between 13 and 17, and then they have this different set of ads for 18 to 25, and then 18 to 24, and another set of ads for like 25 to like, I don't know, 35 or 40 or something, and then another set of ads. Like they just have these arbitrary cut points, and so it's arbitrary. We'll put 17-year-olds in one category and 18 in another category. Okay, people less than 25 in one category and people older than 25 in another category, and things like that. And these are just kind of arbitrary cut points. Maybe there's a reason behind them. I don't know. Okay, so cut points, where to put them is a little bit arbitrary, right? And there's not a clear-cut way to do it. All right. There's a function called cut, and you can just say, like, I want something around like 4 bins here, okay? And so here I just have a bunch of numbers 0 through 11, and I've added a bunch of random noise. And so cut will kind of produce bins, and you can ask R to fit a linear model between Y and the cuts, and it does this, and this is kind of the resulting fit. Okay, so here's just some data, and it just says, okay, well, let's fit the data like that. Okay, and so here I've just done predict based on kind of the sequence there. Is that all right? So this is just kind of step functions, right? So it's an option. You don't have to fit step functions, but you can. All right. All right. But I think this is kind of the most, I don't know about exciting as far as today's lesson goes. But now we can talk about basis functions and regression splines. Excuse me. All right, and so the basis function so this is kind of a generalized form of like an additive model, okay? And so with polynomial function, okay, polynomial function is a regression is a form of using the basis function, where the basis function b1 is just x, and the basis function b2 is x squared, and the basis function j is x to the j power, okay? And then the step functions, the basis functions were basically like the indicator function for this interval and the indicator function for this interval, because it's still in this form, right? Beta 0 plus beta 1 times some kind of function, beta 2 times some kind of function, okay? So this is just kind of like a little bit more of a generalized form of linear regression, except here we're saying we've got not just the variable x, but we've got some kind of function applied to x, okay? And so what we're going to do is we're going to say, okay, well, you know what? Let's say, let's allow these things to be like little piecewise polynomials, right? And so you might have something and you can say like, oh, maybe I want to fit like a cubic function to this portion. We're going to create little cut points, or we call these things knots, okay? And we say like, okay, for the data in here, I'm going to fit a polynomial thing, and for the data in here, I'm going to fit a polynomial thing, and the data here, we're going to fit a polynomial, something like this, right? Now, the issue with this is that I guess these lines should have gone to the green boundaries, but they might not be continuous at kind of the borders of these things, right? So that's not like a desirable property, right? Generally, you want something continuous, so we can say like, okay, you know, you were this value when you were 17, and when you were 18, you get this value, and when you're 19, you get this value. And we want that to kind of be a smooth thing, and we don't want this jarring thing where it's like a huge discontinuity, right? I mean, the step function, it's definitely not continuous, right? But, you know, maybe we want something continuous. So, so one thing we can do is we can kind of put some constraints to kind of make sure that they are continuous at the knot, okay? But here, even if we do that, we might get something where it's not smooth, right? So the first derivative here is not going to be defined, and that could present its own kind of problems. And so here it's continuous at the knot, but it's not smooth. So maybe we don't want, and so ideally what we want is we want something where it's at the knot, it's going to be continuous and smooth, okay? So how can we do something like this, right? How can we make sure that, you know, I'm going to fit a function over here, and I'm going to fit a different function over here, but I want to make sure that at the knot, it's going to be continuous and it's going to be smooth, okay? So what are the properties of derivatives for something that's continuous and smooth? Like, what has to be defined? Yeah. Okay, the derivative has to exist, right? And basically, the second derivative has to exist at that point, right? We have to make sure that we have a second derivative. And if we've got this kind of if the second derivative is continuous, you know, the second derivative doesn't have to be smooth, but if the second derivative is continuous, then that will ensure that the first derivative exists everywhere, and if the first derivative exists everywhere, then it will be at least a smooth function. So this is what we've done, okay? So we're still using the basis function form, okay? Except our basis function is going to be this, okay? This is our basis function. And this is what we call a truncated cubic basis, all right? This is fancy words. Don't worry about it, okay? Basically, we are saying that we're going to create a knot. This is a xi. I don't even know how to write this, okay? By hand, like when you write notes, like this was I always hated when this symbol showed up in the notes because I never knew how to like write this by hand, right? It's like, it looks like an E, but with this tail at the bottom. Okay, so anyway, it's xi, okay? Anybody know how to write this by hand? How it's supposed to look? Okay, this is just what shows up in the thing. Okay. Okay, and so basically, for values greater than xi, it's going to be x minus xi cubed. Okay, so that's basically so the basis function is kind of like if you've got this thing, and this is I don't know if that's xi right there. Okay, so basically before xi it's 0. Okay, all right, and then at xi you get a cubic function. Well, that's not quite cubic, right? So this part is like x cubed, but it's technically x minus xi cubed, and over here this is just x, or not x. This is just y equals 0 over here. Okay, right, and so this thing is smooth. Okay, this function is smooth because as you come in from the left, the derivative is going to be 0, and as you come in from the right, the derivative is 0, right, here. So the derivative is smooth there, and then so we've got this. Okay, so I'm not going to save that. Okay, and so if we look at this and we look at the first at the basis function at xi, okay, h of x is 0 coming in from the left and 0 coming in from the right, so it's continuous. At the first derivative, this at xi, it's 0 from the left, and it's going to be 0 from the right, so that's also there. Okay, and if we also look at the second derivative is also continuous. Okay, at xi it's going to be 0 and 0. Okay, so this is how we're going to kind of ensure that the thing is going to be smooth and continuous. Okay, and so kind of to illustrate this, I've just made some dots here. Okay, 1, 4, 15, 40, 85, 100, 95, 85 or something. Okay, so this is just some dots here, and I'm going to try to fit a cubic basis function with a knot at 4. Okay, so I'm going to just put a knot here at 4, and so there will be 4 terms to fit. Okay, we're going to have x1, x squared, and x cubed. Okay, starting at x1, x squared, and x cubed. So that's kind of a cubic function, and then we're going to fit a cubic basis function starting at 4. Okay. And so at the knot, when x is 4, again the function, first derivative and second derivative will all all equals 0. This is technically for the basis function. I get it. This should say, we can see at the knot the basis function, first derivative of the basis function, and second derivative of the basis function all equal 0. I got to fix that there. Okay. And thus the function, first derivative, and second derivative of the original function y all remain continuous, even though we're adding a piecewise function at the knot. Okay, and then if the second derivative is continuous at the knot, then the function is smooth at the knot. Okay, and so kind of just did the little bit of math. So if we did the function, the basis function at 4 is 0, the derivative of the basis function at 4 is 0, and the second derivative of the basis function at 4 is 0 as well. Okay, and so so if the values of x are 1 through 8, then x squared is 1, 4, 9, 16, 25, 36, 49, 64, and x cubed is going to be 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, so on and so forth. And the way it works for h of x, the basis function, is basically it's 0 all the way over here, and then at when x is 5, it's basically 5 minus 4 is 1, 1 cubed is 1. Okay, at 6, it's 6 minus 4 is 2, 2 cubed is 8, and so on and so forth. Okay, and so this is basically what we are fitting. And then we just say, okay, let's fit a linear model between x squared, x cubed, and the basis function, and it does this. Okay, And then, and here we can just make predictions by doing this. And so for the predictions, I'm taking the sequence and I'm subtracting 4 and I'm cubing it. And then for anything where s is less than the not 4, I'm just manually forcing it to 0, okay? And then if I do this, I get this smoothed out function, okay? So this is a nice smooth function, and this is technically, we've got a cubic fit right here, and then we're adding a cubic basis function over here, and by doing that, it remains smooth, okay? That's kind of neat, I think. I don't know. Maybe you're not as excited as I am, okay? But just by kind of doing this simple thing, which I think this is a clever idea, okay? It's a piecewise thing, but by kind of just making sure that it's, you know, 0 everything to the left and this to the right of the knot, you end up always making sure that's going to always ensure that the resulting function, even though it's piecewise, where, you know, from 0 to 4 it takes on this form, and then from 4 and higher you're adding something piecewise to it, the function remains continuous and smooth. Okay. And so you can keep doing this and make things more complicated by adding more knots and things like that, and you know, whatever you do, you're going to get a smooth function there, okay? The natural cubic spline is a little bit similar, but they add some constraints to make sure that the endpoints become linear. The math gets messy, and I don't really remember how it's done. So I'm not gonna, let me see. Okay, let me see. Natural cubic spline. There's something. Spline. Oh, geez. Yeah, okay. Don't worry about it, right? So, somebody else figured it out, and they've implemented it in R, and you can do it, right? So if you had to do a basis spline manually, you could, but of course nobody does this manually. Nobody goes through this process of stuff. We just say, R, fit a cubic basis spline for me, right? We just say basis spline or cubic spline. We just tell it, do literally, you fit, the function is called BS for basis spline. Oops. Wait. Oh, library gam. Okay, library gam. Okay, and then BS is the basis spline function. Okay, and then NS is the natural spline function, okay? And they're very similar. It's just with a natural spline, it's going to make sure that the endpoint is linear, and this endpoint is linear. And I guess that might be a desirable thing if you're thinking of extrapolating, right? Because if you're going to extrapolate, it's probably better to extrapolate linear than cubic, but well, I don't know. Okay, don't extrapolate. That's the rule at the end of the day. Okay, but everybody does it. Everybody wants to predict the future, but don't. Okay, give us statisticians a bad name. Trying to predict the future. Okay, don't try to predict the future. You'll only be right if you're lucky. I shouldn't say that, but okay. yeah, there's library splines, there's library GAM for generalized additive model. And basically, you can just say, I want to fit a linear model between y and basis spline, where we're going to have 4 knots or something like that. Oh, I'm sorry, not 4 knots. So the knots thing here is the location of the knots. Okay, let me. So if so, knots is the internal breakpoints. So here you'd say it's not how many knots you want, but where you want the knots. Okay, so we're going to say I want a knot at 4. Okay, and if I do this, we get this is the basis spline that gets fit when R uses the basis spline function, and we can see that if we did it manually and we did it using R, we get the exact same thing. Okay, so this is when we did it our own way using H, the H function and things like that. And here, don't do it manually. Okay, I did it manually to just kind of show you that it works, but in general, if there's a package that does it and it's regularly updated, use the package. Okay, so that's one of the pros and cons of R, is that there's like thousands of packages, and they're varying quality, right? Some packages are really good, some packages are not, and so kind of a rough guideline is look up the help documentation for the package, right? Go to CRAN and find the thing. And if the documentation was updated in the last year, then you can probably use it confidently, okay? And if it hasn't been updated, then that means it's not being actively maintained, and you shouldn't use that package, okay? So kind of check. CRAN does its own internal audits, and it will kind of make sure that the packages are compatible with the latest versions of R and things like that, and it will remove packages that don't meet its internal audits. But just as a user, you should kind of check the documentation, make sure it's been kind of regularly updated when you use it. Okay, so anyway, BS to fit a basis spline. You can hit natural. You can use NS for a natural spline. Okay, and here we want a natural spline at 4, and with 1 knot, I guess if you impose the constraint that it has to be linear at the end, it can't do much, and this is what you end up getting. Okay, so you probably need to add a couple, like another knot for a natural spline there. Okay, so with a natural spline, I can fit 2 knots, a knot at 3 and a knot at 6, and we get something that looks like this. Okay, so this is just a toy example. Okay, where I've done this, and this is you can hit the summary on the natural spline fit, and this is kind of just, is it significant to include the spline, the knot at 3 and the knot at 6, and so these are basically the basis functions where you have your first basis function and your second basis function, and they both come back significant. Okay. So anyway, so that's what we get. Again, choosing the location and the number of knots, it's not straightforward. It's a little arbitrary. A common approach, and whether this is the right approach or not, I don't know. But a common approach is to just do something like at percentiles. So if you want 3 knots, you do it at the 25th, 50th, and 75th percentiles or something like that. But you can always kind of do some cross-validation and just say, like, okay, here I fit this thing with 3 knots, here I fit more knots, more knots is a more flexible model, right? So more knots, more flexibility. And there's always kind of that question of, do I want a really flexible model, which will generally have what? Low bias, high variance, or do I want a less flexible model, which will have more bias, but maybe less variance? And how do we know what's best? Either we have intuition about the data and we say, well, based on my experience, we should have knots here and here and here. Or we just say, I don't know, let's check cross-validation, okay? And I think for better or worse, we often rely on cross-validation, okay? And so, our reliance on cross-validation really is bringing the idea of you want your training data really to be representative of the test data at large, right? And so this is an issue. This is an issue for all sorts of things, right? So basically, when they for like facial recognition stuff, there were a bunch of issues with identifying minority faces because the training data was all based on the data that they had access to, right? And that was mostly people that the training data was not as diverse as the world population at large, and so they got like good performance via cross-validation and stuff, but because the training data was not representative of the data at the world at large, when there were new observations, new cases that didn't quite match the training data, the performance was poor, all right? And so Microsoft, I don't know if you guys remember, like they had that 3D camera thing for their Xbox. Does that thing even exist? Do you guys remember this thing? It was like the Xbox 360. So that's like, I don't know, how many years ago now? 10 years ago now or something? They had this like 3D camera and it would like recognize your face and recognize like where you're standing in the room and stuff. But basically like it had trouble recognizing minority people, and they were like, this is racist. And kind of unintentionally it was. It ended up unintentionally racist because it was a fault in the training data that they used. Okay, and we have to just be aware of that. Okay, be careful. So anyway, cross-validation is great, but it really depends on your training data being representative of the world at large. Okay, so. Okay. So now we have another kind of spline, right? Like how many splines do we need? But this is the smoothing spline, okay? And the smoothing spline is similar to fitting a natural cubic spline, okay? Where you've put a knot at every single location in the data set, okay? And you're like, no, that's too many knots. And yes, absolutely. If you just said natural cubic spline with a knot at every single data point, yes, you would absolutely get too many knots, and it will fit your data like perfectly and gets too wiggly. Okay, so the smoothing spline combines basically the natural cubic spline along with kind of like ridge regression, a penalty for being wiggly. Okay, so ridge regression, you penalized big coefficients of beta, and lassa, you penalized any coefficients that were not zero. So basically, it's kind of like this. It's this shrinkage method where you say, all right, let's, so when you fit a regular spline, you're saying let's estimate kind of the coefficients for the kind of the different basis functions using least squares regression, right? So you say like, okay, let's fit this by minimizing the squared residuals, and we're doing the same thing, except now we're minimizing the squared residuals plus some penalty for having too wiggly of a function, okay? And so so we attach a penalty to the second derivative, which is, you know, the measure of the curvature here, okay? And so so regular least squares fit to some kind of function. You know, you minimize this, the squared residuals, and this time, okay, this g of x is kind of the fit function, and this is the result of the kind of the natural cubic spline where you put a knot at every single point in the data set, okay, which is way too many knots, okay? But we're saying, okay, let's do this thing with way too many knots, but in order to prevent the super kind of wiggly, overfit, way too flexible model, we're gonna penalize if it's too much flexibility, okay? And so we say, so now we, you know, we attach basically a shrinkage thing to the second derivative of the function. Does that make sense? So it's similar in concept to the ideas of like ridge regression and lasso, where we say, okay, we want to minimize the RSS, we want to minimize the squared residuals, but we also have a penalty for having this undesirable thing. And in ridge regression, the undesirable thing was very big betas. For lasso, the undesirable thing was betas that were not zero. So now we're going to say minimize the RSS, but penalize large second derivatives, okay? So if the second derivative, you know, you integrate the second derivative, so it's kind of like the cumulative sum of the second derivative. So we're going to penalize large second derivatives. So large second derivatives means there's high curvature in the function, right? It's how quickly the first derivative is changing, which means, you know, how quickly is the slope changing. If it changes rapidly, you're going to have a big second derivative, and that gets penalized, right? And then so this lambda is how much penalty do we apply to this thing, right? So if lambda is huge, it's going to really penalize wiggly curves, and if lambda is not big, the penalty is a lot less. Is that okay? And all right, yeah, so if lambda is 0, there's no penalty for curvature, and that's the equivalent to using a natural cubic spline with knots at every x value, and that's going to be terrible. Okay, it's going to be way too curvy. Okay, and then if lambda is infinity, okay, then it's going to penalize anything with any bit of curvature, okay? And so it's going to basically force a linear regression fit, okay? Because a linear regression fit will have no second derivative, and so it's going to fit basically a straight line fit, okay? And then so, you know, everything in between is going to be something between a wiggle and a straight line, and again, what value of lambda do we pick? I don't know. We probably use cross-validation. It's so terrible that that's my answer to everything, but that's probably what we end up doing, okay? And so anyway, R makes this very easy for us, okay? We do smooth spline, okay? This is the function that we use, all right? And we say, all right, this is my kind of my x, and this is my y, and you don't in R you don't define the size of the lambda. You say they use a degrees of freedom fit, okay? But basically, larger degrees, more degrees of freedom corresponds to smaller lambda, more wiggle, okay? and fewer degrees of freedom corresponds to larger lambda, so less wiggle, okay? And so here, here's degrees of freedom 8, or small lambda, degrees of freedom 3, larger lambda, and this is kind of the fit that we get. And I should what is this? Yeah, I need to. It should be smooth. I don't know why I know why, because I drew it wrong. But you would have a. Let me go back and redraw this thing. Okay, so let me do wiggle predict, which will be predict on. So I need S to be a sequence from. What is min cars.speed and max cars.speed 4 to 25. Okay, sequence 4 to 25 by equals 0.01. Okay. Will this work? Okay, let me just try that. S comma X and Y differ. Okay, I want okay, this should do it. What's going on? Okay, sorry. Why is my okay, I gotta figure this out later. Predict smooth that spline. Okay, I'm sorry. This is not working. All right, I get it. Another day. Okay, well, anyway, you get basically a wiggle, a more wiggly fit versus a smoothed out fit with the colors don't match up, but more degrees of freedom produces a wigglier fit there. Okay. I'm gonna just keep going, and maybe we'll just end a little bit early today. Is that all right? Instead of taking a break? Okay. All right. So that's fitting the smoothing splines. And basically, yeah, if you have too many degrees of freedom, you're going to be fitting basically a natural cubic spline with a knot at every single x. Okay, and then so the other thing we'll talk about is local regression. Okay, and so local regression is, well, what did I write? Basically, you are fitting a regression model to just a localized window of your points, okay? And it's, I guess it's non-parametric. It's like sort of parametric. Technically it's non-parametric because you get no, you don't have a parametric fit. You don't have this nice functional form when you do local regression, okay? So like linear regression, you get this nice functional form. It's beta 0 plus beta 1 times x1 plus beta 2 times x2 and so on and so forth. When you do local regression, you don't get that, okay? You're not going to get any kind of fit like that. You just get kind of predicted values for everywhere. And the way it's making predicted values is using basically local weighted linear regression, okay? So low S is locally weighted scatter plot smoothing. I guess it came out in the late 70s, okay? And basically what we're doing is we're fitting just a few points at a time. That's the local part, okay? And then the way we do it is we fit weighted least squares regression. Did you guys learn weighted least squares regression? Okay, so we think we remember. Do we remember how? So what does weighted least squares regression? How does this work? How is it different from regular old least squares regression?
So the variance of the errors is called
Okay. Yes. The let me see. Okay, so at a simple level, the way weighted least squares regression, how that is different from regular old. Let me just. Okay, so if you have like points that look like this, regular old least squares regression wants to minimize the residuals everywhere, right? So it doesn't want any of these, so it's going to fit something like this, okay? Now, with weighted least squares regression, okay, if you have something like this, okay, if you apply heavy weights here, and low weight and low weight, okay? What happens is that the regression line will try to minimize the residuals. Oops. What's going on here? Okay. These touch screens. All right, something. Okay, the regression line is going to basically try to minimize the residuals through these points, okay? And it's going to say, it's okay if I have a big residual over here, okay? And on the other hand, if you have something, if you have high weight, high, and then low, and this is a point, and this is low weight, and this is high, the regression line will try to minimize the residuals through the high points, okay? So, so the weighted regression says, you know, these points are more important than these ones, okay? We want to make sure we keep these points happy and that that when we make a prediction, we are that the mistakes for these points are small and the mistakes for the other points, they can be big, all right? So weighted regression kind of says like these residuals are, I don't know, these points, and their residuals are very important, okay? It's like giving special treatment to certain data points in the data, okay? Which could make sense for something like, you know, when you went out and you collected data, maybe you had like really precise measurements for certain people, and then the other ones you were kind of guessing, right? And in those cases, if you know where things are very accurate and you need to kind of match it, you might say, I really want to have very little residual for this point. My model needs to predict these people very well, because these people I know are accurate and they're representative. And these other ones, like, it's okay if the residuals are bigger because I'm not even sure if this measurement was taken accurately or something like that, right? So that's kind of what weighted regression does. It says these residuals are more important. We want to minimize these residuals. That's more important than minimizing these other residuals. Regular old ordinary least squares says all the residuals are equally important, and we don't want very big ones, right? The squared residuals are penalized. Okay. So what local regression does, I got it. Something happened with my graphs here. Okay. So here is the data. Okay, I've got 1, 2, 3, 4, 5, 6 data points, and if I fit a linear model to it, this is kind of the fit that I would get. Okay, and so and then, you know, you can get the coefficients. This is the intercept and this is the slope, and this can be obtained by doing kind of your regular old what are your matrix operation, right? X transpose X inverse X transpose Y, right? We should have this memorized by now, tattooed on your body, okay? And if I did X transpose X, X transpose Y, we would get these coefficients like that, right? Okay, so with low S, okay, you can just do this in R. So I'm gonna do this manually. Again, don't do it manually, right? Just use low S in R. It's gonna do a good job, right? And so anyway, if you do it this way, this is the fit that it gets, okay? So you don't get a nice straight line, you get just this kind of, this curve here, okay? So how did we get these segments here? Okay, so there's technically like 6 segments that are joined together. Each of these segments are found by doing basically weighted least squares regression for kind of a window of points, okay? And so when you do weighted least squares regression, you basically have a matrix of weights W, and you do X transpose WX inverse, X transpose WY, okay? So the weights kind of say like these points are more important than these points, okay? And so basically, I'm just kind of saying when we do the local regression, we draw kind of like a window around certain points. The point in the middle of the window gets the highest weight of 3. The points next to it get a weight of 2, and the points that are, you know, a little bit farther away get a weight of 1, and everything else gets a weight of 0. Okay, so kind of so our diagram looks something like this. So here basically I'm fitting linear regression to these 3 points. Okay, this point gets a weight of 3, a weight of 2, and a weight of 1. And these points get a weight of 0, okay? And so for this thing, we're gonna fit like a linear model just on these 3 points, a weighted linear model, and we can see that this line really does try to minimize the residual here, and it's okay if the residual is bigger for this point and this point, and these points don't matter because the residual on this thing is like crazy big, and the linear model would never do that, right? But because it's weighted and it's only on these 3 points, the local thing, we get a fit here, and we can see that this fit basically lines up with the lowest curve right there. And then and just to kind of illustrate that indeed, if I fit the weight matrix to 3, 2, 1 here, I'm going to get the coefficient of 0 and 2.8. Okay, so this has an intercept of 0 and a slope of 2.8. And I can do this for the other points in the thing. Okay, and so for this one, the window is centered here, and we have the points next to it. So this gets a weight of 3. These 2 points get a weight of 2. This point gets a weight of 1, and these points get a weight of 0. Okay, and so it tries to fit those, and when it does, it gets this line. Okay, and then just moving on, it does something similar here. We're going to put a weight of 3 here, a weight of 2 here, and a weight of 1 on these points, and we fit weighted least squares regression here. And we do it for the other ones, and we can see that each time we do it, we get something that fits kind of the lowest curve very well, right? So this point gets a weight of 3, these get weights of 2 and weights of 1. And so if I draw all of these together and compare it to the low S, okay, so the low S curve is in red, and then when I did my manual weighted least squares regression on each window, we get something where each segment kind of lines up very closely to what low S is doing. Okay, now of course, don't do the manual weighting and the stuff itself, and it doesn't line up perfectly because I think R does something ever so slightly different from what I'm doing, but pretty much this is what it's doing. It's fitting. It's just saying, okay, let's look at this selection of points located centrally around here. We're going to have higher weights in the middle, lower weights as we go out, and 0 weights for everything outside of the window. Okay, and then it kind of pieces them all together to kind of create this smooth-ish curve. Okay, and this is not truly smooth, but this is basically what it's doing. Okay, so here is like I fit a bunch of weighted least squares regression lines manually, and R basically did the same thing and pieced them all together to get the red curve there. And so that's low S. Okay, so how does this work? And I didn't finish my notes for this part, but okay, so the generalized additive model basically says, all right, let's just let's combine these things together. Okay, so it's kind of like a linear model, or a multiple linear model, except we don't have to have linear relationships. We can have any of these kind of smoothed out relationships. So maybe we want to fit a spline relationship between whatever variable it is and the output, right? So here we're looking at someone's wages and their age, okay? And this is like the original data, and we're gonna say, you know what? I know wage is not linearly related to age. I'm not quite sure what I should use. Should I use a cubic polynomial? Should I use a different kind of thing? I'm not quite sure, but you know what? Let's just fit a spline function, or in this case it does a local fit, so it basically does low S, okay? And so with low S you have kind of these different parameters, these spans, which kind of define how wiggly it ought to be, okay? And so with a small span it gets more wiggly, and with a larger span it's smoothed out. And so we can just say, you know what, let's fit a linear relationship between age and weight. Not linear, I'm sorry. Let's fit a smooth kind of non-parametric relationship between age and wage, okay? And we can do this, okay? So we're just, rather than doing this, we're using some arbitrary functions, okay, that are not necessarily linear or things like that. So we're doing some kind of smoothed out function here, and so this is the functions that we have on year and the functions that we have on age, and education actually is categorical, so we're just probably fitting you know, a categorical kind of a dummy encoded thing there, okay? And so we don't have to have these things, and it's additive, so we just say, all right, let's just add these things together, okay? And so so here we've done this with natural splines, okay? And over here we've done it with smoothing splines, okay? So very similar. We're just saying, like, should I use a natural spline or should I use a smoothing spline? But basically the idea is, like, these relationships between wage and age and wage and year don't have to be straight line linear relationships anymore, and they don't even have to be nice polynomial fits. They can just be kind of this arbitrary smoothed out function, okay? And then we add them together to get our generalized additive model. And so the nice thing about the generalized additive model, or the GAM, is that it still maintains a high degree of interpretability, okay? So we can say things like, there is this relationship between age and wages, okay? Except it's no longer linear. So we can't just say every time somebody gets older, we expect their wage to go up. But you can present this picture, and this is interpretable, right? We can say this is the effect that age has on wages. And as, you know, people go from 20 to 40 years of age, we expect their wages to go up and up and up and up, okay? And once they hit around 40 years, we expect their wages to kind of plateau. They've kind of reached the peak of their career and they're not going to get any better, right? And then once you go past 60, your wages go down because either you've retired or you're, you know, working some kind of junky job or something, right? So this kind of picture still maintains interpretability, okay? We don't have a simple, like, every year you get older, this is what happens, okay? But the picture of the relationship between age and wage is still interpretable, in that we can say this is the kind of relationship that exists. And I don't think people have a hard time understanding something like this, because we encounter stuff like this all the time, like height, right? Height, you get taller as a kid every single year. As an adult, you stay the same height, and maybe in your old age, your bones deteriorate and you get shorter or something like that, right? So we're accustomed to not always having a linear relationship everywhere, and we can kind of illustrate each individual relationship with the variables here, okay? And so that's the kind of the advantage of using this generalized additive model, is that we can fit the nonlinear relationships, which means we might be able to make more accurate predictions, and, you know, we can examine the effect of each x on y if everything else is fixed, okay? Smoothness can be summarized via degrees of freedom, okay? The limitation with GAMs is that we are restricted to additive models, okay? So at the forefront, interactions will not be included. Now, you can manually include an interaction term. You can kind of multiply two numbers together, and you'll have kind of an interaction term, and you can throw that in there. But it's you know, it's not designed for that right out of the gate, okay? And it kind of requires you to do some kind of manipulation there, right? So, and depending on how the interaction terms go, you know, it can be complicated. You know, this multiplicative thing is probably a lot easier if it's like one is a continuous variable and the other one's categorical, and that like you can say like this is kind of what happens when the person is male, and this is what happens when the person is female, right? Maybe the relationship between age and wage is different for males and different for females. We don't know, okay? But the generalized additive model is not really designed for interactions right out of the gate. You can do interaction terms, but you've got to basically create a new variable on your own by kind of multiplying them together to do that, okay? And so the GAM is best suited for regression type of problems because it's kind of this additive nature. But again, if you wanted to, you can take the additive part and plug it into a logistic function and make it a classification thing, right? So you can go from classified as 0 to classify as 1 by putting it into the logistic function, right? So this is the logistic model, the generalized linear model, the GLM, where you have the linear model and you put that into the kind of the logistic function. And here you can just do kind of the same idea, except instead of the linear model, you're using the additive model, where you're having these non-linear functions of each variable, and you throw that in there, okay? And so you can do that and have something done there for wages, okay? And that's that. That's for chapter 7, okay? So we can so chapter 7 kind of is again all about non-linear relationship things. So you don't have to keep the linear thing. We can kind of extend that, which is very useful for a lot of real life situations because we don't always have these clean-cut linear relationships all the time. Okay, we'll end there. Have a great weekend, and or what's that? Well, I mean it's Wednesday, but I don't think anything goes on, right? Every day, every week's a 4-day weekend. It's pretty great. So, all right, we'll see you guys on Monday, okay?